Okay, let's dive right into this explainer and build out your analyst toolkit to really demystify the math behind simple linear regression. Whether you're trying to figure out if an ad campaign actually drives revenue or if capital expenditures really predict a company's return on assets, simple linear regression is the foundational mathematical engine that makes all those insights possible. It's literally how we move from just guessing to actually knowing.
Here is our blueprint for today. We're going to cover 1. The OLS model, 2. The 4 assumptions, 3. ANOVA and goodness of fit, 4. Hypothesis testing, 5. Making predictions, and finally 6. Functional forms. Let's get into it.
Section 1. The OLS model, building the machine.
So the crucial point here is that this tool lets us test hypotheses about two distinct variables, using one to predict the other. We have a dependent variable, that's our target metric, like stock returns, and an independent variable, our predictor, like market index returns. The ordinary least squares, or OLS criterion, is basically the mathematical mechanism we use to find the perfect straight line through our data, and it does this by minimizing the sum of the squared residuals.
You can see this perfectly illustrated right here. When we map return on assets against capital expenditures, we're drawing a line of best fit right through the data points. Now, the vertical distance from each observation to that line, that's a residual. The OLS machine is calculating the exact slope and intercept to make the total sum of the squares of all those vertical distances as tiny as mathematically possible.
Moving on to Section 2, the 4 assumptions, the safety manual.
Before we rely on this machine, we gotta check the safety manual. These 4 core assumptions are the strict rules our dataset absolutely must follow for the regression to be reliable. First, linearity. The relationship between the variables has to actually be linear. Next up, homoskedasticity. Third is independence, meaning our observations aren't correlated with one another. And finally, normality, which just means our regression residuals need to be normally distributed.
Now, homoskedasticity is quite a mouthful, I know, but if we strip away the jargon, it simply means the errors in our predictions don't fan out into a cone shape or cluster wildly as we move across our data points. We need consistent random errors to ensure our standard errors and ultimately our conclusions remain totally reliable.
All right, Section 3. ANOVA and goodness of fit, running diagnostics.
This analysis of variance, or ANOVA table, is honestly the absolute best way to organize all of our math. It shows exactly how total variation splits up into the variation we can actually explain and the error we can't. The sum of squares total sits right at the bottom. Our model decomposes that total into the regression row, which is what our model successfully explains, and the error row, representing the unexplained leftovers. By looking at the ratio between the mean square regression and the mean square error, we derive our F-statistic. This is the ultimate test that tells us if our model as a whole is statistically significant.
But the real so what here is the R-squared value, also known as the coefficient of determination. You get this simply by dividing the regression sum of squares by the total sum of squares. In our ROA and CapEx example, this number proves that a massive 80.01% of the variation in return on assets is directly explained by capital expenditures. I mean, that is an incredibly strong fit.
Section 4, hypotheses testing, field testing the model.
So, here is the million-dollar question. Just because we drew a nice line through our data points using OLS, does that relationship actually hold statistical weight? Is there truly a real relationship there, or did we just connect some random noisy dots?
To answer that firmly, we use a t-test to check our slope coefficient. We want to be sure our independent variable genuinely impacts the dependent variable. You literally just take the estimated slope and divide it by the standard error of that slope. If the resulting t-statistic falls outside our critical confidence bounds, boom, we can confidently reject the null hypothesis. We've just mathematically proven our slope is significantly different from 0.
Section 5. Making predictions, forecasting the future.
Okay, let's break down this step-by-step procedure. First, you find your target number by plugging your forecasted independent variable right into the regression equation. But as we know, a single point estimate just isn't enough. Next, you got to gauge your potential error by calculating the standard error of the forecast. And finally, you wrap that estimate in a prediction interval so you know your exact margin of safety. This lets you say with maybe 95% confidence that your future value is going to land somewhere between two specific bounds. Just keep in mind, this margin of safety actually widens the further your forecast moves away from the historical mean of your data. Finally, Section 6, functional forms, upgrading the machine.
Because let's face it, the real world doesn't always move in a perfectly straight line. If your data curves, kind of like this revenue and advertising scatterplot we're looking at, a basic straight line is going to leave obvious error patterns. It completely misses the natural arc of the data, which means our predictions out at the extreme ends are going to be wildly inaccurate. No good.
So to fix this, we upgrade our toolkit using functional forms. We're essentially transforming our variables with natural logarithms to wrestle that curved data back into a workable linear regression. We generally have three main options: log transforming just the dependent variable, just the independent variable, or both. A log-log model, for example, is incredibly useful when you want to measure the elasticity between variables. We simply test these out and choose the form that gives us the best R-squared and the most random rule-abiding residuals.
Ultimately, just as the source notes right here, your goal as an analyst is always to minimize that standard error. You want to get your predictions as close to reality as mathematically possible. Whether you're using a standard straight line or a more complex log-log transformation, you are always trying to shrink that distance between your model and the real world.
So, now that you're armed with OLS, a firm grasp of those four assumptions, and the flexibility of functional forms, what invisible market trends are you going to uncover next? The predictive power is totally in your hands now. Thanks so much for joining me for this explainer, and have fun analyzing your data.